Hello and welcome. I am Dr. Pauline Fu. In this video, I will go over residue analysis for regression. I will look at the first question. If given the residue plot as below, interpret those residue plot or what could be the problems with the module, with the regression analysis. Okay, let's look at the first diagram. So this is a residue plot. This residue plot looks like a parabola. Okay. So there's a pattern. So that means it is not linear relationship between x and y. See this parabola curve. Okay. So this is a curvilinear, maybe quadratic model would be appropriate. Okay. So now second one, the second one is the residue plot against the predicted y, because this is y hat, okay, y hat. And this plot has a pattern. As y hat increase, the residue also increase. So it's like the fan-shaped. Okay. So that means unequal variance exists. Okay, so unequal variance. So that is not a good residue plot. Oops. And next one is the residue. Y minus y hat means residue. Residue against independent variable x. This is a 3 standard deviation, negative 3 standard deviation. And this residue plot, this part looks good. Okay, this part, the residue spread evenly. But here we have outliers. So this number beyond negative 3 standard deviation, this is an outlier is here. So when you do analysis, you might want to remove this outlier, then you do the analysis. Okay. So next one, this is the y-axis is the residue. X is the predicted y hat. And this residue increased, then decreased. Over here, decrease, then increase. So residue has pattern. That means equal variance is violated. Okay, the assumption of equal variance is violated. And this one is like the histogram or frequency distribution. So this one, it looks like skewed to the right. Okay, so it is not normally distributed. Okay, so this is this question. And the next question. A navy base is considering modifying or adding to its fleet of 48 standard aircraft. The final decision regarding the type and number of aircraft to be added depends on a comparison of cost versus effectiveness of a modified fleet. Consequently, the naval base would like to model the projected percentage increase Y, so percentage increase Y in fleet effectiveness by the end of the decade as a function of the cost of X. A first proposal is the quadratic model, EY equal to beta 0 plus beta 1x plus beta 2, this is x squared. beta 2x squared. The data is in this table here. Question A, fit the model to the data, and then construct a residue plot versus X. Okay. Do you detect any trends, any outliers? Question B, do you have the inferential points? Okay, inferential points. So there are two questions. So this is the data. Okay, so this is Y in this column and X is in this column. Okay. So I will combine question A and question B together. So I will use SPSS to do quadratic analysis and then produce some graph. Okay. All right. So where is my SPSS? It is here. Okay. So this is the data. So I'm going to modify this data a little bit so that we know which one is Y, which one is X. So that is Y, and this is X. Okay, and then we are going to use quadratic function. So go to Analyze, Regression, Curve Estimation. So after that, this is original data. When you open it, dependent variable is Y. Dependent variable is Y. Independent variable is X. And we are going to use quadratic. So take away the linear, quadratic. And then make sure you check out the constant in equation. Okay, plot models. So that is this one, and quick display ANOVA. ANOVA table, that's not necessary. So I just click OK button. So fit the model. So where's my output? It is here. So this is the quadratic, okay? And where is my model? So I'm going to copy this one. To OneNote so that I can make annotation. So I'm going to put the result here. Oh, it's way too small. All right. So should be look good. And then where is my model, quadratic model? Remember to write down the model. You need the parameter. So I'm just try to increase this one so that you can see clearly where is the parameter. Parameter estimate is here. Okay, so we see the parameter exit. So this is the constant. It is actually beta 0. Okay, this B1 is actually the same as beta 1, B2, beta 2. Okay, so based on this parameter estimates, we can write down the model. So EY equal to beta 0. So 10.659. Okay, beta 1 is negative number, negative 0.282 times x, and beta 2 is positive 0.003 times x squared. So this is the model, quadratic model to fit the data. Okay. So next we are going to create a scatter plot. Okay. So go to graph, legacy diagram, scatter plot. Just click the simple and then define y, x is the cost. Okay. And then click OK button. So this is the scatter plot. Okay. And this scatter plot is modeled by this curve here, quadratic curve. Okay. But how do we produce a residue plot? Residue plot. To create residue plot, you can do this. Analyze regression, and then curve estimation. Do I have plot? Not here, so I'll go to the analyze regression, and then linear. So y is dependent variable, x is independent variable, and then from here you click plot. Okay, check out the histogram and check out the normal probability plot, and then create a standardized Z residue plot. So this is the Z put into the, this one here, residue, okay, standardized residue, okay, into Y, and this is the predicted Y, standardized predicted Y, like Y hat, but it is standardized, okay, so this one goes to X, okay, and then based on these three graphs, one is histogram, and then normal probability plot, and then the residue plot is here. Okay, we can see if the assumption for regression is met or not. And click OK button. So this is the histogram. Okay, obviously this is not normally distributed. It is skewed to the left. Okay, and over here we have a normal probability plot. This one looks okay. The normal probability plot is on the straight line, close to the straight line. Okay. And the last one here, scatter plot. So this one is the standardized residue. Standardized residue versus standardized predicted value. Okay, and this one again looks like you have the pattern. Okay, so decrease then increase. That's why the curve, the quadratic model is suitable for this one. Okay, so that is this question, And the next one, we are going to have similar questions here. Maybe I want to copy the, do I need output? Oh, I think I'm okay. So next question. Maybe I will get some output for future reference. So this is the scatter plot, standardized, and this is normal probability plot. So I'm going to copy these three charts. Okay. Control C. And then, oops. Normal probability plot. Not enough. And the last one is the residue plot, standardized residue plot. Okay, so I will adjust the picture size later. Okay, so now let's move on to next question. So again, this question is about urban air samples, chemical engineering. Do I need to increase font size? Let me see. This part. Okay, now it's better. Chemical engineering at Tokyo Metropolitan University analyzed urban air specimens for the presence of low molecular weight decarboxylic acids. The dicarbolic acid as a percentage of total carbon and the oxidant concentrations for 19 air specimens collected from urban Tokyo are listed in this table. Okay, so here we have y variable. Okay, so what is y? The percentage as total. This one is y variable. And the oxidant concentration is X. So this one is X. Okay. So the question, this is the raw data. So what is the question here? Okay, so I will write down the question. The question is, consider a straight line model relating to straight line model. Okay, the question is construct a straight line model. Construct a straight line model between y and x, and then assess the validity of the regression assumption. Assess the validity of the regression assumption. So that is the question. Okay. So let's do the linear regression first, then use graph to assess the assumptions. So I have this data ready in SPSS. This is a Novi fleet. Try to locate my data. Here. All right, so this is the data. Okay, you have Y, you have X. Okay, oops, what did I do? Okay, just go to the data view. All right, so go to Analyze, Regression, and then Linear. So I already did this. I will just click Reset button. Dependent is Y, independent is X. Okay. Now we want to assess the assumptions of the regression. So you check the plots. Y, you use Z residue, standardized residue as Y, and use standardized predicted value for X, Z, okay, predicted value for X, and check out the histogram, check out the normal probability plot, and then click OK button. Click OK button again. So now, see this chart. So first, let's get our model. So our model is based on the coefficient. This is the constant, and this is the coefficient for X, based on these two numbers. Okay. And then, so I'm going to copy this first, so that I can write down the equation. I'm going to put the right. So the equation is based on, this is our beta 0, this is beta 1. Okay, so the equation would be EY equal to beta 0, so negative 0.24 plus 0.2. This is beta 1 times X. So this is the linear model. And next, let's analyze the assumptions. So the assumption is the histogram looks normally distributed. See, okay? And so I'm going to just copy this one into here. Adjust later on. And then this is the normal probability plot, looks like on the straight line. Okay, that means it is normally distributed, the error. Okay, the residue is normally distributed. And this one is the scatter plot. This is a very good scatter plot. The points are spread out evenly without any pattern. This is one. Second, no point are outside 2 standard deviation, negative 2 standard deviation. Okay, so based on these 3 diagrams, we conclude the assumptions are met. Okay, so just copy this one to here. Okay, so this is a question about construct a linear model and then assess the assumptions of this linear model. Okay. Last question, Duban-Watson test. So where is the question? Yeah, this is the question. So this question has overlapped with the previous one. I'm just trying to see if I can move down a little bit. Okay, now looks better. All right. So, but just adjust my computer. All right, so now I can see the complete question. All right, so, but this graph is on the way. This graph is on the way. I'm going to move a little bit. Okay, great. Okay, revenue generated by a new pill, a leading pharmaceutical company that produced a new hypertension pill would like to model annual revenue generated by this product. Company researchers utilized data collected over the previous 15 years to fit the model. Okay, E, Y then subscript T. So it's like this one here because so the model should be E, Y subscript T. Okay, subscript T. So Y subscript T represents revenue in year T. Y subscript T represent revenue in year T. Okay, so equal to beta 0 plus beta 1 x and then subscript T. X subscript T represent cost per pill in year T. And then plus beta 2 time. T is time in year. Okay, year 1 until year 15. Okay. So this question, as we can see, has a variable, time as a variable. Okay, another variable is the cost. Okay, so this could be a time series data. Okay, multiple regression for time series data. So the company statistician suspects that the assumption of independent errors, remember the errors have to be independent, that is one of the assumptions. The assumption of independent errors may be violated and that in fact the regression residues are positively correlated. So the researcher conclude the residues are positively concluded. To test this claim at 0.05 using Duban-Watson statistic, D is given 0.776. Okay, so the question here, you are given Duban-Watson test statistic D 0.776. Okay, And then, do you believe the residues are positively correlated or not? This is the question. Okay, so to do that, we are going to write down H0 and H1. Okay, no hypothesis. So H0 said residues are correlated. Okay. No residue, I'm going to type up. So H0 states no residue correlation. That is H0 correlation. And alternative H1, so this is H0. H1 said positive residue correlation. So I have H0, I have H1. And how do I test? You use compare critical value with the test statistics. And then how do you find the critical value for Duban-Watson test? To find the critical value, you need sample size n. In this case, it is 15. The data is over 15 years. And you need the variable, you need k. K represent number of independent variables. In this module, we have cost is one variable. We have time is another variable. So total we have two independent variables. Okay. Alpha is also given. Alpha equal to 0.05. So based on these three numbers, we look up the table. This is the table here. Okay. So this table is critical value for Duban-Watson test when alpha 0.05. In this table, identify k equal to 2, sample size equal to 15. So we get DL equal to 0.95 and DU 1.54. Okay, those two numbers. So once we get those numbers, and then we compare the given test statistic 0.776. So 0.776 is smaller than this DL, smaller than this number, DL equal to 0.95. Okay, and when you have D smaller than DL, okay, this is lower tail test. Because of this, you reject H0 because test statistic smaller than DL. Okay, so this number smaller than DL. Remember DL we look up in table is 0.95. Okay, and when D smaller than DL, we conclude reject H0. Reject H0. So H0 is here. No residue correlation. We reject this one in favor of the positive residue correlation. Okay. So in summary, we go over some questions about residue analysis. The assumptions are the error are independently the errors are normally distributed, and the errors have equal variance. Okay. So only when those assumptions about residues are met, then you can go ahead with regression analysis. Thank you so much for your attention. I look forward to see you next time.